as I'll be talking about my recent results on asymptotic movements of pattern random matrices. So let's begin. So the main object here is such shapes inside a unit square in R2. Given a nice enough shape called the pattern, we will create random matrix which looks like the given shape called the approximating matrix and study its asymptotic behavior. Okay, so I have given you a shape, but I have not shown you how its matrix looks like and what is its approximating matrix. And in the title, the term that we mentioned, pattern random matrix, is the same as approximating matrix here. So these are the same things. So let's go over some examples. This is a triangle pattern where we have a triangular region inside a unit square, and on the right hand side we have its approximating matrix, and intuitively it looks like just like the pattern. Next, we have a smaller square inside unit square, and this is a filled square, and the approximating matrix for such a shape is given on the right hand side. So the entries, non-zero entries, which are all random and IID, have the same similar shape as the given pattern. So this is on the right hand side is the approximating matrix for the pattern on the left. And we have a general construction on how to exactly construct such matrices which look like the given pattern, and they can be constructed for all sizes of matrices. And what we are going to do is to look at their asymptotic limit in the sense of distribution, so and see that those limits converge. So basically these such matrices, as I increases their size and if I fix a pattern on the left and I increase the size of matrix on the right, I will have more and more entries. And asymptotically, what will happen is that their eigenvalues will almost surely start looking the same, at least follow the same histogram. So, okay, that's our introduction. So we have proved that the movements of the pattern random matrices converge asymptotically. And the asymptotic movement of the pattern random matrix is equal to the integral of a combinatorially defined function called the path counting function. So we will make all of this precise. So starting with some background. We'll start with the Wigner semicircle law. Let xn equals 1 over square root n xijn be a random matrix such that for all I less than equals to j, xijn is IID standard Gaussian random variable, and for all I greater than j, xijn equals xjin. And this makes xn a symmetric random matrix and hence has real eigenvalues. We call such a random matrix xn Gaussian orthogonal ensemble GOE. Let small tr xn equals 1 over n trace of xn denote the normalized trace of matrix xn. Then the theorem states that let xn be a sequence of GOE random matrices, then limit as capital N goes to infinity, expectation trace of xnk equals to 1 over 2 pi integral minus 2 to 2 t to the power k square root 4 minus t square dt. It looks like a lot of like an equation which is hard to decipher, but if we look closely, then on the right hand side, these are kth movements for a probability distribution called the semicircle law. So this is the density for such a distribution for square root 4 minus t square over 2 pi. And if I take t to the power k and multiply with its density and take the integral over its domain, it's the kth moment for a given probability density. So on the right hand side, we have kth moment in the traditional sense of a probability density function. But on the right, what we have is the kth moment. It's a different thing. It's different type of moment. Kth moment of a random matrix. The term on the left is referred to as the kth moment of random matrix, and it says that asymptotically, the kth moment of GOE random matrices exists and is equals to the kth moment of Catalan number. Although both of these moments have underlying equivalence, like expectation trace X and K can actually be written as moments against certain measure, and in the limiting case, it is the moment of semicircle law, but we'll not go into details. Okay, so what is the power of this theorem is that it says that as the size of matrix increases, GOE matrices, its histogram look more and more like semicircle. And that's what happens for a 5,000 by 5,000 random matrix, which is GOE. Before getting into our results, we will shortly look at what DT operators are, because these operators gave us motivation to look into this project. Dykema and Hagerup introduced DT operators as distribution limit of certain upper triangular random matrices with diagonal entries mu distributed, where mu is compactly supported measure and off diagonal being complex Gaussian. So it's clear from the figure above, matrices look something like this. These are they mentioned an upper triangular version, but it's the same as saying what happens for lower triangular matrices, which look like this, where on the all the off diagonal entries are complex Gaussian IIDs, and on the diagonal we have mu distributed IID entries. Okay, these operators exhibit nice properties, such as having spectrum equals the support of measure mu. These operators include Voisilisco's circular operators. These operators exhibit interesting combinatorial properties, which were further studied by Snidey. And these are our DT operators. How did they motivated us to do what we have in our results? Is that these are the random matrices which follow a certain pattern, which is a triangular pattern. But we asked the question, what if we give our favorite choice of shape inside a square, inside a unit square? So, and we then later find out that, okay, given the boundary of that shape behaves nicely, and that means the measure of the boundary is, say, 0, then in those cases, we can make sense of such a matrix which looks like the given pattern and call it approximating matrix. And its moments do exist. Okay, with this, now let's go to the definitions for what we need to state the main theorem that we have. For a positive integer n, let square bracket n be the set of positive integers 1 through n. Let S be a subset of unit square 0, 1 cross 0, 1. It is called a pattern if the Lebesgue measure of the boundary inside the unit square is 0. So note that this measure is two-dimensional measure. So the boundary needs to be really bad in order to not satisfy these conditions. So given a subset of this unit square, the boundary needs to be really bad. And by that, I mean it should have non-zero measure inside the unit square to not be a pattern. Otherwise, in most nice shapes and even non-nice shapes, the boundary do tend to have zero measure. So given a pattern S, a positive integer n, and ij inside square bracket n, let Sij n equals the pattern S intersected with a small square, which is given by the product of interval j minus I over n, comma j over n with n minus I over n and minus I plus 1 over n. Let xij be IID random variables with finite moments of all order, having mean 0 and variance 1. Here, mean 0 is a necessity. If we take non-zero mean random variables, then the behavior is different for what we are studying. So mean 0 is a necessary condition, but variance 1 is just for normalization. So we can actually take a sequence of random variables which have a variance different from 1. And with all this information, we can create a matrix out of a given pattern. So given a pattern S, we define its approximating matrix, also called the pattern random matrix X and S, to be a random matrix of size n by the following formula. So ijth entry of the random matrix X and S is given by 1 over square root n xij if the set Sij n has non-empty interior. And it is equals to 0 if Sijn has empty interior. Okay, again, just to clarify, here is the example. So what's really happening is that we have random variable appearing if the square, so we divide this whole thing into square grids, into the pattern into a square grid of size n by n, and on each square we look if that square intersects with the given pattern, and wherever the square intersects with the given pattern, we plug in a non-zero IID copy of random variables. So that's how we create this approximating matrix. Okay, next we define configuration. A finite sequence in formal variables x and x star is called a configuration and is denoted by cx x star. As an example, x star x star x star is a configuration. Note that this is non-commutative, so we do not have the same configuration if we permute the entries. Length of the configuration is the length of the sequence. For example, for this configuration, the length is 6, because there are 6 times x or x star appears. Ck denotes the kth element in the configuration C from the left. For example, C3 is x star for this configuration x star x star, because x star appears at third place from the left. Okay. Now we define what start movement is for a random matrix. Given a configuration C x star and a matrix X, let x to the power C denote the evaluation of the matrix X under the given configuration, where x star is the adjoint of the matrix X. So evaluation of x and x star under the given configuration. And the meaning is clear from the example. If configuration is x star, x star, x star, these are small x's, formal variables, then x to the power C is the same as taking product of the random matrices according to the given rule. So we just plug in x and x star, capital X and capital X star in place of small x and x star, and multiply them together. That's my x to the power C. For a square matrix of size n, let small tra be the normalized trace. Given a matrix X, its start movement under the configuration C is defined by expectation trace of x to the power C. So given a configuration C, I take its product. I take the product of x and x star according to configuration and take trace of it and then find mean of it. That's the start movement under configuration C. And these are the objects which we want to study and their limiting behaviors as the size of matrix goes to infinity. Because these objects store, well, without an expectation here, if we just take the trace of x to the power c, these do store information about the spectrum of the matrix. Okay, let's look at the main theorem. The main theorem that we found states that given a configuration C of length 2n and a pattern S, the limit as n goes to infinity, expectation trace xn sc equals 1 over n plus 1 factorial integral over n plus 1 dimensional cube 0 1 to the power n plus 1 of this function f sc n plus 1 x1 up to xn plus 1 dx. So in this theorem statement, the left hand side here gives the movement, starred movement for the pattern random matrix, and asymptotically it says that the limit exists for a pattern random matrix, and the limit is actually integral over a specific function which is obtained, which is unique given a pattern S and a configuration C, and you just take the integral of this function and we get the required output. But we have not yet defined what this function is, and that's what our major task will be in next section. Fsc n plus 1 is called the path counting function and is defined combinatorially. So let's jump to some combinatorics. A path is a function I from m plus 1 to n, such that I of 1 equals I of m plus 1, which says the endpoints should have the same value. So the graph here shows the graph of a path from 9 to 5. So it starts at 3 and takes some values, and then at the same point 3. This is a little different from textbook definition of path, where we do not really restrict its endpoint, but for all our purposes, we do have the restrictions to have the same endpoint. So I call them path. The things on x-axis, which are the points in domain of the path, are called indices or index, and things on y-axis, which is the points in codomain of the path, is called a color. The kth edge of a path I is the set ik comma ik plus 1 for k inside M. For example, the third edge here is this edge. It's simply the third edge, and by edge we mean the collection of y values. So it's the collection of 2 and 4 that gives us the third edge for this path. A social path is a path in which every edge appears at least twice. Okay, is this social? This clearly is not a social path, and because the fourth edge, which starts at 4, so this edge doesn't appear again anywhere. And by appear again, I mean there is no other edge which has the same endpoints. So this is not a social path. Let's look what a social path might be. It's coming in next slide. So before that, okay, let's just probably say that. For example, every path here is a social path, because look at any edge. There is another edge which has the same endpoints in all these cases. Okay. Now we'll look at the starred movement again. The starred movement under the configuration C of the random matrix X and S has a trace expansion of the form expectation trace X and S C equals 1 over capital N M by 2 plus 1 expectation of this sum. So what's beautiful here is that out of each term inside this sum, xi1, i2, to the power C1 up to xi-im-i1 to the power Cm, we can recover a path which is obvious from the indices. So to each product term of the form xi1 i2 dot 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 xim i1, we associate a unique path I from m plus 1 to n, given by I at kth place is just the I sub k value from the subscripts of x here. And we set im plus 1 equals I1 so that we have the same endpoints. We call this path I to be the path derived from product term xi1 i2 up to xim i1 in the trace expansion of xnsc. So xns is the pattern matrix. If I take the configuration at the top, then in the trace expansion we get such terms, and out of every such term we get a unique path. And also we can see from here that given a path we can uniquely recover a product term in the trace expansion. Okay. So we define a couple of more different types of paths, and then we will say what path counting function is, which was given in the main theorem. So a path I from 2n plus 1 to n is called strictly polar paired under a configuration C if every edge is paired to exactly one other edge where one of them is starred and the other one is unstarred. What do we mean by this? So look at the figures here. A and B are non-examples of strict polar paired paths, while C and D gives the examples of strict polar paired paths. To see what's happening here, so we have in figure A, the configuration is x star, x star, x star. Not going into details, but if it is x, then the first edge is blue. So the edge becomes blue if it is just x, and it becomes, I have colored it red if it's x star. That's what it means for a path to follow a configuration. That's like pictorial representation. So here we have x and then x, so blue, blue, and then x star, which is red, red. So this in figure A, this is not a strictly polar paired path. And the reason is that the pairing is not strict. So every edge is paired to 3 other edges. We want exactly one other edge which appears, and that's a strict requirement. So this is not strictly polar paired. In B, we do have strict pairing happening. Like this edge, first edge and second edge are the only ones with the same endpoints. But in B, what we do not have is that starred and unstarred movement. The star and unstarred edges are not paired together. Here, star, unstarred, first unstarred entries are paired together, and then both the star entries are paired together. That's not what we want. What we want is something like, see, this is an example of strictly polar paired path. Here, the pairing is strict. So there is just one edge which appears. So there is just exactly one other edge which appears, which is the same as a given edge. And the pairing is polar. So given a blue edge, there is a red edge which it is paired to. So that's what we mean by polar pairing. And D is also an example, but it's in a different configuration, x star, x star. So blue, red, blue, red. Here, the pairing is strict, and red is paired to blue every time. Okay. Now these are the paths which became central in our results. Polar constraint path. A path I from 2n plus 1 to n is called a polar constraint path under configuration C and pattern S if the path follows the pattern and configuration of the matrix X and S. That is, it is a path derived from a product term in the trace expansion of X and S C with none of the random variables identically 0 in the product term from which the path is derived. So what does first point says? First point says that if we look here, then the path that we get from the subscripts should be such that the product term is not identically 0, which means none of the random variables here is identically 0. So we are looking at only the paths which gives a product term where none of the entries is identically 0. That's my first condition on polar constraint paths. The second condition is that these paths should pass through n+1 colors, which means cardinality of the range of path is n+1. And the third condition is the paths should be strictly polar paired, as we defined in the previous slide. And if all three conditions are satisfied, we call such a path polar constraint path. Now, these are the paths which are the product terms corresponding to these paths are the ones which actually contributes to asymptotic moment calculation of pattern random matrix. That's the central observation that we had. So let's look at an example of polar constraint path. This is an example. It's strictly polar paired, and it follows all the conditions that it goes to exactly 4 + 1, which is 5 colors, because it's a path from 8 + 1 to 5. 8 is 2 times 4, so there is 4 + 1, 5 colors it passes through, and given this pattern S0 1 square, which is the whole unit square, and this configuration x star, blah blah blah, this path actually is a polar constraint path. Okay, so path counting function, that's what we had in the definition of in the main theorem. Given a pattern S inside unit square and a configuration C of length 2n, we define a function in n+1 variables called the path counting function. For distinct x1 up to xn-1 points in unit interval, FSC n+1 x1 up to xn+1 counts the number of paths I from 2n+1 to n+1 with the following constraints. The path I is strictly polar paired and passes through n+1 colors. For k inside the set 1 to 2n, the ordered pair xik, xik + 1 has to be inside S if ck equals S. C was the configuration. If kth entry is just x, then this tuple of points have to be inside the pattern S. And if ck is x star, then the reverse tuple xik + 1, xik should be inside the pattern S. So with these two conditions, path counting functions called count all the paths which satisfy these two conditions when we fix x1 up to xn+1 input variables. So it counts the number of paths. We set fn+1 as c, x1 up to xn+1 equals to 0 if any of the entries are same. So in the definition above, we did not mention, but we want all x1 up to xn+1 different. So if they are different, then this is what this function does. It counts the path which satisfy 1 and 2. But if any of the input entries is same, we just let it to be 0. Okay. Now that we know the path counting function, let's go back and look at the theorem again and try to prove it in 2 lines. So give a sketch of the proof. The main theorem is given a configuration C of length 2n and a pattern S. The starred movement, asymptotic starred movement of a pattern random matrix is given by integral of the path counting function normalized by n+1 factorial. And let's look at the sketch of the proof quickly. So the movement, starred movement, is given by this trace expansion, as we have seen before. So this is a sum over all possible paths from 2n+1, from small 2n+1 to capital N. If you look at this carefully, so I can rewrite this sum as sum over polar constraint paths and sum over non-polar constraint paths. Okay, this is easy. But what's interesting is that the polar constraint paths, if the path is polar constraint, then this whole term inside becomes 1 every time, because each of the random variables is associated to another random variable which looks like this, and this happens for every random variable independently. So we get variance times variance times variance, and variance was given to be 1, so it's just 1. And I not polar constraint. Sorry, I should have mentioned here that I has to be social as well. So this sum, because for non-social paths just vanish. So in this second equality, we do not count non-social paths. We count over only social paths. Sorry, I did not write down social paths here in the subscript, but we are counting over only social paths, because non-social paths have one independent term occurring, and we know the mean is 0, so that the moment has to, so the expectation has to be 0. So it's just social paths which are not polar constraints. So second term is bounded. All the terms here are bounded by some uniformly by some capital M, and it so happens that if I is not polar constraint and is social, the number of such paths with relative to n to the power n plus 1 goes to 0. So this whole term goes to 0, and hence we have the theorem. I have written inequality here, but it's a strict equality because this term is actually 0 in limit, and this term's limit is also 0. So that's the proof, and thank you. I think I went beyond the time. That's short. Thank you for this.
Thanks a lot.